Okay, so hello everyone. Let's get started with our environmental engineering class. Okay, so this class we're going to talk a little bit more about the materials and energy balance. So the corresponding reading on your textbook is going to be chapter 4, and I also feel that this is probably the most important chapter that you will use in like throughout the class. Okay, so this is mainly because we're going to use this similar concept when we really apply the let's say our chemistry into the design of the, let's say, the wastewater treatment or drinking water treatment or air pollution control devices. Okay, so again we'll do a quick recap of our last class. So last class we mainly discussed the chemical kinetics, right? We said that chemical equilibrium just means the ultimate state, but we never discussed how fast it is going to take or how long it's going to take for the system to reach to this final state, which is the equilibrium. So to understand the chemical kinetics, we have to find out what is the reaction rate. And we said that the reaction rate is defined as the minus dc dt, right? This is the reaction rate. And we said that there can be different types of reactions that have different types of reaction rates. So there can be zeroth order, first order, second order reaction. Basically, this is just going to be equal to Kc to the power of something, right? Zeroth order means it's to the power 0. First order, then you change that to 1. Second order, you change that to 2. And we also discussed the reaction rate constant. So reaction rate constant is basically a constant value at certain temperature. And we mentioned that the higher the temperature, the larger the reaction rate constant, which means that reaction is going to happen faster. And we also introduced the simplified equation to calculate the reaction rate at any temperature. That is going to be K2 equals K1 theta T2 minus T1, right? And theta can take values of 1.0 something, right? It has to be larger than 1 because only when it's larger than 1, then you're going to have the situation where the higher the temperature, the larger the reaction rate constant. Reaction rate constant. And then we started to talk about the mass balance. We basically give the simple scenario where it's involved or where it's involving the grocery purchase. So this is the example about how many potatoes are being balanced in this entire system. And we find out the general mass balance equation, which is accumulation equals in minus out minus reaction. We also give the mathematical description of this mass balance equation, right, which is V dc dt. This is the accumulation, right, in terms of mass, equals Q in C in minus Q out C out minus R multiplied by V, right? So the R is the reaction rate. One thing we didn't do is actually to find out what is the unit on both sides, right? So basically, in order to let this reaction or this equation to work, we have to make sure that units on both sides are consistent. So if we just take a look at the unit, right? So V here is going to carry a unit of meter cubed, right? And then C, I'll just write it here, C is going to be mole per liter, or let's just use mole per meter cubed, right? And then you divide that by second, right, by time. So basically on the left-hand side, it's just going to be mole per second. This also makes sense because we're talking about the accumulation of mass or of number over time, right? So it's going to be number per time. So if we look at the right-hand side, then Q has a unit of meter cubed per second. This is flow rate. And then C is mole per meter cubed, right? It can be meter cubed or liter, right? But overall, if we use the standard unit, then it's going to be meter cubed. So it's going to be the same, right? And it's going to be the same here, which is meter cubed per second, and then mole per meter cubed. So it's the same, mole per second. And finally, it's the reaction. So in terms of the reaction, we introduced here is going to be what? dc dt, right? So it's going to be mole per meter cubed per second, and then multiply by meter cubed. Okay, so these two will get canceled out. Then that's going to be mole per second. So on both sides, the units are consistent, which is mole per second. Okay, so we also need to pay attention to this because sometimes when you build up the mass balance equation, right, especially when the reaction is not first order, then sometimes you may be losing one parameter here, for example, not considering rate constant or not considering the volume here, then you are going to have a different type of equation. And the way to confirm that the mass balance equation is still valid is to check the unit on both sides, right? So I think you are going to get some practice in your homework on this aspect. Okay, so this is again an overview of the mass balance. How did we derive that? And you get the first example where we can ignore the reaction, and where you have accumulation just equals in minus out. And then the typical example that people use is the primary clarifier, where you don't have any reaction going on in this system. It's just the particles or suspended solids getting settled down, right? Under this situation, you can calculate the accumulation, the basic accumulation of the suspended solids, by just using the inflow of the suspended solids minus the outflow of the suspended solids, right? So now we discuss the scenario where we have the accumulation equals in minus out. But can it be even more simple? It can, right? So when the system is under steady state, which means that the concentration, right, or the conditions are not changing with time, then it means that the accumulation term is even zero, right? So if accumulation equals zero, then you just have the simplified mass balance equation where in equals out. So then you may think, well, this is too easy, right? So it's just whatever you put in equals whatever you get out. But sometimes it can be quite complicated. And one example is the physical mixing process, right? So here I just give an example of the physical mixing. So we know that in the northern states where the weather is very cold, and then when there are snowfalls, right, settling onto the ground, to help with the traffic, people also add salt onto the surface. So as the temperature warms up, then what will happen is that you're going to form some discharge or wastewater that contains a lot of salt inside, a high concentration of salt in the snow melt, right? And this snow melt will just go through the sewer and eventually get discharged into our environment. So this example actually tries to estimate how does this snow melt actually affects the salt concentration in the natural water, right? So here is the problem condition, right? So basically you have a storm sewer carrying a snow melt with 1.2 gram per liter of the salt. And then it's discharged into a stream with 20 milligram per liter of salt. So you see here are two concentration units, right? So although when we discuss the units for the mass balance, we use mole per liter, but it doesn't matter because mole is consistent with the mass, right? So it can be mole per second. It can be gram per second too, right? So basically, these are concentration units, right? Or I would say the mass concentration units. And then if you directly compare them, there's 1.2 gram per liter, and there's 20 milligram per liter. Right? So although 20 is bigger than 1.2, but actually the units are different. And you can see the concentration in the salt discharge is actually much larger than the salt concentration in the stream, right? Because that's why the snow melt is being discharged into the cleaner stream water, right? So to convert the gram per liter into milligram per liter, you need to multiply that by 1,000. Right? And then at the same time, the problem provides you with the flow rate of the two streams or two liquids, right, or two flows. So the flow rate for the snow melt is 2,000 liter per minute, and the flow rate for the stream is 2 meter cubed per second. Again, these two are different units, right? So that's why this problem may get a little bit sophisticated when you directly consider the numbers. So here you have liter per minute, and here we have meter cubed per second. So if you directly look at the number, again, 2000 is bigger than 2, but here, actually, for the stream flow, it's using meter cubed. That is, will make this flow rate to be 2000 liter per second. And again, here it's using per second, while here it's using per minute, right? If you consider everything to be per minute, then you need to further multiply this flow rate by 60 because you're considering the flow rate over a longer time. So further, this problem assumes that the system is at steady state. And then if you look at what it's asking for, right, it wants you to calculate the salt concentration after the complete mixing. So if you directly look at this problem, everything may look a little bit, I would say, mixed up, right? So many conditions, so many concentrations and flow rate. So easier way is to just write out or draw a schematic diagram, right? So let's assume that this is the flow for the salt, and then this is the flow for the stream, right? So then the snow melt, or let's say the snow melt has the condition of, let's say, of salt equals 1.2 gram per liter. So here I use SE mainly to represent sewer, okay, or the sewage. And then if you look at the flow rate of the sewer flow, then that's going to be 2000 liter per minute. And then at the same time, you have the condition for the clean stream flow, where ST stands for stream. So CST is 20 milligram per liter. And then QST is 2 meter cubed per second. Okay, so it's asking what is the concentration. What is concentration after complete mixing? So let's assume that this is Cm. Okay, so this problem basically involves the physical mixing of two streams. So one thing we can do is to just draw a control volume on imaginary boundary. So there are two inflows and one outflow. So this perfectly fits for our mass balance, where you don't have any accumulation because everything is under steady state, right? So which means that dc dt just equals 0, right? And then at the same time, you have the inflow and the outflow. And then we can just put in the conditions and then try to make the mass balance work. But in order to make the mass balance work, we need to also find out how to express these in and outs, right? So we said that the inflow is actually Q in, C in, and outflow is Q out, C out. So you see it needs both the concentration and the flow rate, right? And here you have concentration and flow rate for the inflows, but what about the flow rate for the outflow? Let's say Qm. So now we have to use the mass balance, right? The mass balance tells us that the total mass flow of the water or of the solution has to be the same. So that's why if you have the sewage flow to be 2000 liter per minute, and then the stream flow is 2 meter per second, and then the total mixed flow is just by adding these two together. So you have Qm equals QSE plus QST. And then you have 2000 liter per minute plus 2 meter cubed per second. So to complete this calculation, we have to make sure that they're carrying the same units. So now if you look at all of these units, it looks like we have milligram, we have gram, we have liter, we have meter cubed, second, or minute. So let's just try to find a unified set of units. So normally in water treatment, as we introduced earlier in our class, people will use milligram per liter as the concentration unit, mainly because the constituents in the water are relatively dilute, right? So their mass concentration is relatively low. And then liter is a small volume that people can normally manage. And at the same time, in terms of the unit for the time, let's just use second, right? So because of that, we can do the conversion here. So then you have 2000 liter divided by 60 seconds, right? And then plus 2000 liter, because meter cubed converted to liter is 1000, and then per second, right? 2,000 liter per second. So if you add them up together, so you can cancel this. So that's basically 203.3, okay, liter per second. So this is the total flow. Let's see. Also, it's 233 instead of 203. Oh, it's 2033. Okay. So basically, this is the flow rate. Let me just quickly confirm the total flow rate. So 2,000 divided by 60. Okay. So this is the total flow rate. So then we can build up the mass balance for the salt, right? So you have basically QSE, CSE plus Q stream, C stream should equal to QM after mixing multiplied by C mixing. So now if you plug in the numbers, so QSE is 2,000 and then divide by 60, right? Because you want to use liter per second. And then CSE is 1.2 multiplied by 10 to the 3 milligram per liter, right? And then here you have 2,000 liter per second multiplied by 20 milligram per liter. And then Q is 2033 liter per second multiplied by Cm. So if you plug in everything, you can find out that Cm is basically, let's see, 39.3 milligram per liter. Okay, so this is the concentration of the salt after the physical mixing. So you can see, well, although the concentration of the salt stream or the sewer stream is relatively high, but because the flow rate of the sewer stream is much smaller compared to the, let's say, the stream water, so the entire or the total impact of the salt in the sewer is not that significant, right? It just doubled the concentration of the salt in the water, which might be quite significant in terms of the ecosystem in the stream water, right? So that's why for the sewer water, some of the wastewater treatment systems also treat the sewer water before you discharge them directly into the environment. So again, here, this is showing you how to draw the schematic diagram, right? And then to select this control volume here, right? And then if you plug in everything, you can find out that total concentration or the final concentration of the salt after mixing is 39.3. Okay, so this is the condition where you don't have accumulation or you don't have the reaction. So everything becomes quite simple, that you just have in equals out. So now if you consider what we have discussed or what we have covered, right? So this is a complete mass balance equation. So we said that when there's no reaction, just accumulation equals in and out. The primary clarifier can be the example, right? So suspended solids getting accumulated in the primary clarifier. When there's no reaction and no accumulation, then physical mixing of the water is the typical example. So these two examples have the same commonality that you don't have reaction. So what if there are reactions, right? So how do we solve the problem when reactions are being introduced into the mass balance? So if we talk about the reactions, then we have to consider this reaction kinetics, just like what we discussed last class, right? So we also mentioned that in environmental engineering, most of the time, we'll just assume it's a first order reaction, which means that the reaction rate is K multiplied by C. Okay, so because of that, remember the reaction term is represented by R multiplied by V, so you can just directly plug this in to show this reaction term. But in terms of the systems that have reaction included, then people also try to generalize the typical features that's happening in these systems, and then we created names for different types of the systems or different types of reactors. So in our class, we're just going to cover three types of reactors where mass balance is involved in these in these chemical reactions. So the first type is the batch reactor. So some people also call it as the CMBR. So in the textbook, it's also called CMBR. It's continuously mixed batch reactor. Continuously mixed batch reactor. Okay, so the second one is CSTR, is continuously stirred tank reactor. Okay, so the third one is the PFR, is a plug flow reactor. So we'll cover these three reactors one by one, okay? So you'll find out that actually we use these different types of reactors or generalized type of reactor in a lot of the pollution treatment devices. So first is a batch reactor. So as the name sounds, so batch reactor let the reactions happen in batches. So what happens is that you can find a container first or a reactor first. So first, these reactants are being introduced into this batch reactor. We can assume that there's no reaction during this pouring process. And then after the solutions are ready, then we have a big stirrer that starts to mix all of these reactants and let the reaction to happen, right? And then after that, after the reactants are being consumed or being converted, then we can discharge them and then they go to the effluent. Okay, so in this process, the reactions will happen in batches, right? So you cannot add further flow into the system while the reaction is taking place. So you may think, well, this is too simplified, right? So it's an idealized situation. So are there examples of the batch reactor? I would say a typical example is just cooking, right? If you think about your you're cooking a meal, although a lot of the cooking process is just physical mixing, but there could be chemical reactions taking place, right? For example, if you're boiling tomatoes, then the vitamin C's are being damaged, right? So it's the same process here where you have a pot here, and then you add all the ingredients, and then you start to warm it up or cook it, right? At the same time, you use a stirrer to make everything even, right? Well mixed, and then eventually discharge them and put it onto the table, right? So if you consider the process, you first feed the reactants and then mix and let them react, and finally discharge. So one feature for this batch reactor is that there's no continuous influent or effluent, right? So there's no flow going through the system. So now if you consider the mass balance, right, you have accumulation equals in minus out minus reaction. So we said that there's no inflow or outflow, which means that accumulation is just minus of reaction. Right, so basically it means that the concentration of the reactants is going to decrease because of the reaction. I will further mention that the accumulation can be represented as V dC dt, right? And then the reaction term is represented as V multiplied by R. And further, we assume it's first order reaction where R equals K multiplied by C. So V gets cancelled, and you have dC dt equals minus Kc. So this is quite familiar, right? So this is the solution for the first order reaction. So then you can find out basically the C is going to be C0 exponential minus KT, right? So it means that the concentration is going to decrease exponentially. And it's going to approach zero, but not reaching zero when time goes to infinity. Okay, so this is a batch reactor. And then we can find an example for the application of the batch reactor. So, for example, I think for those of you who are, let's say, who live not mainly in the urban areas, let's say if you live in the suburb, then normally you will see these huge towers, right? So these are the water towers. So basically the water tower are going to store the drinking water that's generated by the water treatment plant, and then when, let's say, when the water treatment plant is not being operated, right? Or let's say if under certain circumstances that people need huge amount of the drinking water, then these water tanks can play a role, right, to provide these extra water. So the water tower are going to just store these extra drinking water. So this problem states that a water tower containing 4,000 meter cubes of water has been taken out of service to install a chlorine monitor. The concentration of chlorine in the water tower was 2 milligram per liter. Right, add chlorine to the water mainly because of disinfection. And also you don't want to put a large amount of chlorine because chlorine is also toxic to human, right? So this level of chlorine is just to make sure that there are no pathogens grown in the water. Okay, so the concentration of chlorine in the water tower was 2 milligram per liter when the tower was taken out of service. If the chlorine decays by first order kinetics at a rate constant of 1 per day, as we know, the chlorine, even if you just leave it in the water, then it's going to react, right? It's going to get oxidized and then get dissociated. So it's going to decay overall. Right, so here it's assuming it's a first order reaction, and here is a rate constant. So remember, the rate constant for the first order reaction is 1 over time. Okay, so it's asking what is the chlorine concentration when the tank is put back in service 8 hours later. So, so this is the first part of the question, and there's a second part of the question. So let's skip the second part first. Let's look at the final condition. Although it's not completely mixed, you may assume the tank is a completely mixed batch reactor. So if we can assume it's a batch reactor, then things will get quite simple, right? So C is just equal to C0 exponential minus KT. So we know that C0, the initial concentration is 2 milligram per liter, right? And then we know the K is 1 per day, right? And T is 8 hours. Okay, so should we just directly multiply these to each other? No, right? Because we have to convert hour into day. And luckily there are 24 hours per day, right? So this just means that 8 hours is 1 over 3 days, right? So in this way, you can directly multiply 1 with 1 over 3, and then you can find out that the final concentration after this 8 hours is going to be, let's see, 1.43 milligram per liter. Okay, so this is the final concentration. So then the second part of the problem is asking what mass of chlorine must be added to the tank to raise the chlorine level back to 2 milligram per liter. Okay, because you are losing this chlorine in the drinking water, right? So the water quality is going to go bad if you don't add additional chlorine back, right? So then how do we calculate that? So if we want to find out the additional mass, right, you need to find out basically how much concentration is being changed during this time. So you need to find out delta C and then multiply that by the volume. Right, the change of the mass concentration multiplied by the volume is a change of the total mass. So then delta C is just 2 minus 1.43 milligram per liter. And then you multiply that by the volume, is 4,000 meter cubed. So now, basically, milligram per liter, you see, we have to make the unit consistent. Milligram per liter is just gram per meter cubed, mainly because 1 meter cube is 1,000 liter, 1 gram is 1,000 milligram, right? So it's going to be the same. So you're going to have 0.57 multiplied by 4,000 grams. So then you're going to have basically 1,000 gram is 1 kilogram. So you can remove this 1,000 here, change it to kilogram. And then you're going to find the final additional mass is going to be 2.28 kilograms. Okay? So this is the final answer for this batch reactor problem. So you can see that in the batch reactor, everything happens in different batches. But if you consider the treatment of the pollution, right? So for example, if you have a wastewater, if you're managing a wastewater treatment plant, then if you consider the inflow of the wastewater, so the inflow is always positive, right? What I mean is that although in different households there can be ups and downs, for example, overnight, then from the residential or from the industry, the inflow of the wastewater is going to be lower. But there are other industries that are generating wastewater overnight, right? So there cannot be certain scenario where you don't have any inflow of the wastewater. So then the problem for the batch reactor is that every time when you operate the batch reactor, you have to cut off the inflow and outflow as introduced here. There's no inflow and outflow. So then you have the problem of, well, you have a continuous inflow of the wastewater, but you have to isolate the reactor so you can let the reactions happen in batches. Then it's kind of like you have to tell the households or the industry that hold, well, please do not generate the wastewater right now because we need to let the reaction happen in batches, right? We cannot do that because there should always be flow going through the wastewater treatment plant, right? So because of that, we have to use a flow reactor. Okay, so the batch reactor cannot hold any flow, right, or accommodate any flow. But in the actual situation where we are dealing with different types of reactants or different types of pollutions, we have to consider the continuous flow or to create this flow reactor. So the same thing for the air pollution treatment, right? If we're trying to deal with sulfur dioxide or nitrogen oxides, the coal is continuously getting burned. You cannot cut off the flue gas and then let the pollutants to react and then connect back the flue gas. It's the same thing here for the water treatment. So here I have the question, can we use batch reactors for pollution treatment? So it's not going to be convenient if we use batch reactors, right? So we prefer those flow reactors. So now you may consider, well, here you don't have inflow or outflow. What if we just dig a hole on both sides and then let the reactants to react within the tank, while at the same time you have an inflow and outflow, right? Can we do that? Yes, we can. So this is the idea for the CSTR, the continuously stirred tank reactor, right? So here you are going to have an inflow and an outflow. So because of that, let's list our mass balance equation again. Right? So you have accumulation equals in minus out minus reaction, right? Accumulation equals V dC dt, and then in equals Q in C in minus Q out C out minus KV or KC multiplied by V. Okay, so the CSTR has two assumptions. Okay, so the first assumption is that everything is under steady state. So if it's under steady state, it means that the concentration is not changing as a function of time in this system. So what that means is that the concentration in the tank, the concentration at upstream of the tank, concentration downstream of the tank, they're not time dependent, right? If they're not time dependent, then you're going to have this term equals 0, right? So you're just going to have in minus out minus reaction equals 0. Okay, so now if you have that situation, then further we know that the inflow and outflow flow rates are going to be the same. So basically you're going to have Q in, or let's just use the same Q. So QC in equals QC out minus KCV. Okay, so the steady state is the first assumption. And the second assumption is that since this is a continuously stirred tank reactor, we just assume that concentration inside the tank everywhere are the same. Let's assume that we have a very powerful stirrer, right? So as soon as the inflow gets mixed, right, or as soon as the pollutants gets introduced into the tank, then they get suspended evenly, and then the concentration everywhere is the same. So if we assume that the concentration everywhere is the same, then the concentration at the outlet, C out, is just going to be the concentration inside the tank. Because at the outlet, there are no more reactions, right? If you consider the outlet location, right? So the reaction happens in the tank. So the concentration at the outlet is going to be equal to the concentration everywhere in the tank. Well, you may also wonder why can't we assume that concentration in the tank is the same as the concentration at the inlet? We cannot, mainly because the reaction is taking place in the tank. So the concentration of the this chemical is already reduced, right? So if we mix the inflow with a lower concentrated, let's say low concentrated chemicals, so the concentration will be lower. So that's why the concentration inside the tank will be equal to the concentration at the outlet of the tank. So if you further have that, then you can replace this C by K C out multiplied by V. Okay, so now you have the relationship of C out and C in. So further, you can divide the Q on both sides. So this is going to be K over Q. So you have C in equals C out multiplied by 1 minus K V. Let me see. Well, this should be a plus sign, right? Because you have the Q in, C in to be on one side, and then you move the other two over there. So this should be a plus sign. So V divided by Q. Okay, so this is a relationship. So basically, the let's say the outflow concentration, C out, is going to be C in divided by 1 plus KV divided by Q. Okay, and further, people define theta as V divided by Q. Then you'll have C out equals C in 1 plus K theta. Okay, so this is a relationship between the inflow concentration and the outflow concentration. All right, so then if you look at this problem now, so remember when we have the batch reactor, right? So the concentration actually decreased exponentially. But now if you have a CSTR, actually convert this concentration into, let's say, a linear relationship, right? Instead of an exponential decrease, now it's a linear decrease. And another thing we need to pay attention to is that if you consider this theta here, so theta is equal to volume divided by flow rate. So because of that, theta is going to carry a unit of time, right? And this also makes sense because remember for K, the first order reaction rate constant, the unit is 1 per second, right, for first order reactions. So that's why K theta multiplied together should be unitless. And the 1 here is unitless. So that's why it makes sense. And then the concentration, the units are conserved. So that's constraint that the K theta has to be unitless, right? So theta has a unit of time. So because of that, people also define this theta as the characteristic time of the system, or people also call it as the resonance time of the system. Because if you consider, if you have certain flow going through this volume here, then the average resonance time is just going to be the volume divided by the flow rate, right? The average resonance time of the water or of the solution going through the system is just volume divided by the flow rate. Right? So that's why we also call the theta as the characteristic time or the resonance time. So now we can do another practice, okay? So this practice involves a water treatment system that's called the sewage lagoon, okay? So I'm not sure if you have seen this sewage lagoon before. Normally they're used for containing the treated water, right? So basically to convert this sewage and then to remove or let the microorganics, or let's say let the bacteria to eat off these organics in the water, and especially when the pollutants in the water is relatively low. Right? If it's heavily polluted water, then the sewage lagoon will not be very effective. So basically, the sewage lagoon look like this, shown in the picture. It is a large pond into which the sewage or effluent from the sewage system flows into. And then the sewage lagoons are also called effluent ponds. The sewage and effluent are broken down by germs in the lagoon. So you need ecosystem to reduce the concentration of the pollutants. The sun and wind play an important role in working of the lagoon, and they provide light, warmth, and oxygen to the water, and this is necessary for the growth of the bacteria in the water. So the more the bacteria, the faster the reaction, right? So you can intentionally add in more bacteria to make the water more active so that you can remove the pollutants from the water or from the sewage lagoon. So this example problem is actually talking about this design here. So we have a sewage lagoon that has a surface area of 10 hectare. So hectare is a unit for the area. So 1 hectare is 10,000 meters squared. So it has a depth of 1 meter, and this is receiving this amount of sewage, right, at certain flow rate. And this is containing 100 milligram of the biodegradable contaminant. So this can be some organics or organic pollutants. At steady state, the effluent of the lagoon must not exceed 20 milligram per liter of the biodegradable contaminant. So what this means is that you constrain the when C in equals 100 milligram per liter, C out has to be smaller than 20 milligram per liter. So further, we assume that the lagoon is well mixed and that there are no loss or gains of water in the lagoon other than the sewage input. So this just means that there are no extra in or out, right? So what about the gradation reaction rate coefficient? So it's asking for this rate coefficient or rate constant must be achieved for first order reaction. So we can assume this is well mixed, right? So this will qualify the lagoon as a CSTR. So what this means is that C out equals C in divided by 1 over KT, right, has to be smaller than 20, or 20 milligram per liter. And at the same time, C in is 100 milligram per liter. Okay, so now things will get quite simplified because you just need to rearrange this. So you're going to have 1 K theta has to be larger than 5. So K theta has to be larger than 4. This K here, which is the reaction rate constant, has to be larger than 4 over theta. So theta is volume divided by flow rate. So volume is 10,000 multiplied by the depth, right? So this is the total volume. And then you divide that, it's 10 hectare, right? So then 10 multiplied by 10,000. And then in the bottom, you have the flow rate, 8640. And then here is meter cubed per day. Okay, so with this condition, you can find out that the theta is going to be so basically theta is going to be 11.57 days, right? And then because of that, then K has to be larger than 0.35 per day, right? So this is how we can use this concept of the CSTR to solve the reaction rate constant. Okay, so this is a CSTR. And finally, the third type of reactor is called the plug flow reactor. And I think I'll leave the description of plug flow reactor in our next class. And this is mainly because here we've gone through two calculation problems. And then normally in the class, we will leave more time for you guys to think about this or to do the calculation. So since this is a recorded class, I probably just shorten that time over there. So please go over these contents, and then also I have left the assignment 3, right? So then you will get some practice regarding these different types of reactors. Okay, so we'll talk about the PFR in our next class. Okay, thank you. Feel free to let me know if you have any questions.